Hello and welcome to this manufacturing process technology part 2 module 39. We were talking about laser machining in the last module, and we were also discussing about what happens to a semi infinite surface under certain boundary conditions when there is a constant heat flux being added to the surface from one of the sides. And in that we had also talked about that if the condition is that the laser beam is of circular nature and the spot size is of circular nature, what is going to be the criteria. So, for that just a quick recap of heat conduction and temperature rise of a circular spot. We wrote the governing equation in this case as del 2 theta zt by del z2 minus 1 by alpha times of del zt by del t equals 0, and the boundary conditions were again written down as theta z0 equals 0. That means the temperature at all the different values of z, assuming that there is only a circular region of diameter, let us say 2d, over which there is a constant heat addition or a heat flux through this particular area. So, as a result of which the variation of temperature in the z direction at point of time 0 when no heat is being added is considered to be that of room temperature. Room temperature is considered to be 0 here, which is the baseline temperature. All the temperature measurements are relative with respect to the room temperature, and also it was further presumed that the temperature gradient at z equal to 0, that means on the surface right about here, as a function of time, with respect to the z direction, was actually again determined by minus ht, where ht would be the quantum of heat as a function of time coming from the circular spot onto the surface, divided per unit conductivity, per unit the area here, which is pi d square by 4, pi capital D square by 4, and per unit time. So, this essentially is, you can say, the heat added per unit area, or the rate of heat added per unit area per unit thermal conductivity of the material, which is actually nothing but the negative of the temperature gradient corresponding to z value 0 at the surface, and time at all instance of time when the laser beam is operating or interacting with the particular surface. So, having said that, we would now we also wrote what are going to be the general solutions for this particular expression, and as I told you that because it is not really a heat transfer class, we would rather prefer to utilize this solution, and it can be done in any manner that the partial differential equation is solved using either variable separation method or any other method. So, this the solutions, the final solutions of this PD, which would really need for investigating what is going to be the depth of melting temperature with respect to time. So, the solutions to this equation becomes theta zt equals twice h root over alpha t divided by k times of the IERFC z divided by twice root of alpha t minus of IERFC root over z square plus capital D square by 4 divided by twice root alpha t. And this, as I think I have already pointed out, it is only an expression of the error function, how this IERFC is sort of treated. So, IERFC of a function zeta can be recorded as 1 by root of pi e to the power of minus square of zeta minus zeta ERFC zeta, where the ERFC zeta is again recorded as 1 minus really the error function of zeta, and I think we all are aware that the error function is nothing but a numerical integral represented as 2 by root pi 0 to zeta e to the power of minus x square dx. So, we calculate the numerical value or estimate the numerical value of this integral for a corresponding variable zeta, and then estimate this IERFC zeta, which we put back here. The zeta in one of the cases is the z or the depth of the melting temperature divided by root of twice alpha T. Alpha is again the thermal diffusivity, which is which we calculated in one of the last steps as K by rho C, the conductivity per unit, the volume specific heat, and T really is the time solution up to which you have to really wait as this theta for a circular spot comes to the melting point of the material which is being hit upon by the laser. So, in a way, for solving for T, you will have to really equate this theta to the theta melting, assuming that there is a constant heat addition on the surface up to an extent of a diameter, let us say capital D. You can try to find out what would be the Z value, okay, as a function of, let us say, all these different parameters, and at a certain point of Z the melting would stop to take place, and that is really the boundary where theta equal to theta m. Okay. So, if theta is theta m, that is going to give you a sort of depth up to which the melting temperature would reach, beyond which the surface would be stabilized. So, that is how you find out the value of the Z or the shape or size of the way that the melting temperature reaches into the material. Okay. So, if we looked at what would happen at, let us say, the value of Z equal to 0. So, if I want to calculate Z equal to 0, so obviously the zeta in the first case, which is the Z divided by twice root of alpha T, becomes a 0, and obviously you can always look at it by looking at the IERFC, which is nothing but 1 by root of pi e to the power of minus zeta square minus zeta times of the ERFC zeta, where again the ERFC zeta is nothing but 1 minus the error function of zeta. So, this value then corresponding to this 0 value of the zeta comes out to be 1 by root pi. This guy eliminates away, this is 1, again this is 0 times the error function of zeta, so this eliminates away. So, we are actually left with only one term here corresponding to Z equal to 0, which is root 1 by root pi or root pi inverse. So, if I were to look at the temperature on the surface as a function of time at surface, the equation would really change into twice h root of alpha T divided by K, which is borrowed from the first part here, right about here, times of this value here, which is 1 by root pi, times of whatever valuation has to be assigned to this particular entity here, IERFC, which I am going to calculate eventually. So, this would lead to an expression which is in 1 by root pi minus of the IERFC d divided by root of alpha T by 4. Already the 2 factor is there, and we are trying to talk about the d square by 4 root, or just capital D by 2, which can be brought in here. I am sorry, this is capital D. Okay. So, that is how you represent the theta on the surface, that is corresponding to Z equal to 0 as a function of time, and this is how you really have to evolve the solution. So, at a certain beam diameter, let us say d equal to a 2 millimeter spot size or 1 millimeter spot size, or even few hundred micron spot size, for a certain alpha value, that is thermal diffusivity value, what is going to be the time in which the theta reaches the theta m is really questioned here, and through which you could actually get a sort of indication of the machining time. Okay. So, here let us say we try to address a numerical problem where there is a laser beam with power intensity 10 to the power of 5 watt per millimeter square, again 10 to the power 7 watt per centimeter square, which we are hitting upon, and it falls on a tungsten sheet, and we take the focus diameter of the incident beam in this particular case to be about 200 microns. So, this is what the diameter d value is equal to, 200 micrometers. We need to ascertain how much time will it take for the center of the circular spot to reach the melting temperature of the tungsten, which is 3400 degrees Celsius, using the presumption that we have just arrived at for a circular spot size. Okay, and given some of the properties of the material, like the thermal conductivity for example, or the volume specific heat C for example, and also given the fact that 10% of the beam is absorbed. Okay. So, let us say if we substitute the appropriate values, we get the value of H, the power density, as 10 to the power 7 watt centimeter square, and alpha is approximately 0.79 centimeter square per second. We had earlier calculated this to be the ratio between the thermal conductivity 2.15 to 2.71, okay, the volume specific heat. This is rho c, this is k, okay, related to the material. So, this is the material property aspect here, 0.79 centimeter square per second. And if we wanted to solve for what is going to be the time of the machining to start with. So, if let us say theta at 0 T, as we know, is going to be theta m for this material to hit upon the melting temperature, where the process will start removing or ablating away the material. As you know, there is always going to be a momentum transfer and spatter by which the melting material is pulled out of the zone of machining. So, this is going to be 3400 degrees Celsius, and we can relate this to twice H root over the formulation is twice H root of alpha times of, let us say, Tm. We assume Tm to be the time that it takes for the surface to arrive at the melting point. So, time for surface to arrive at the melting temperature. So, if that is Tm, so twice H by times of root alpha Tm divided by k times of 1 by root of pi minus I ERFC diameter d by 4 root of alpha t. That is how, so this is Tm again. Okay. So, that is how you go for the value of theta 0 t. Okay. And so, if I were to add the beam power, assuming 10% absorption has happened, the beam power in this particular case would be about 0.1 times of 10 to the power of 7 watt per centimeter square. Only 10% is coupled, the remaining 90% is reflected from the surface, times of the 2 times of this H value times of root of alpha, which is 0.79 times of Tm, and this divided by thermal conductivity 2.15 times of 1 by root pi minus, we have a value IRFC equal to the diameter d, which is in this case about 200 microns. So, we have the diameter here as 0.02 centimeters, and divide this by 4 times of root alpha Tm, where alpha is again 0.79 times of Tm. Okay. So, we do not know the Tm value, and now it is actually upon us to sort of iterate the value of Tm here to have a complete balance between the LHS and RHS of this particular equation. So, that is how you actually arrive at the Tm value. Okay. So, we would now, let us say, like to have the value here, for example, or we consider as beta root of 0.79 Tm, just wanting to write it in a proper manner, so that the zeta value in this particular case happens to be 1 by 200 beta. So, this whole thing can be expressed as 1 by 200 beta. Okay. Let us say this is the zeta in this particular case, and as I already have sort of illustrated earlier, that you know, if I really wanted to write or find the value of the zeta here as 200 1 by 200 beta, I would like to write the IERFC of some value zeta to be equal to again 1 by root of pi times of e to the power of minus zeta square minus zeta times of, now this is 1 minus of the error function, okay, of the value zeta. Okay. So, it all starts from this error function, the numerical integral value of the zeta term. Okay. So, if I wanted to substitute this here and try to look at what is going to be or how this is going to look like. So, the equation we had earlier derived was 3400 equal to twice into 0.1 10 to the power of 7 times of root of 0.79 Tm divided by 2.15 times of 1 by root of pi minus IERFC of zeta. Zeta was given as 100 or 1 by 200 beta here, and beta again I think I had sort of assumed as 0.79 Tm whole under the root. Okay, so I am left with a formulation, okay, where I say 3400 is equal to actually 9.30 10 to the power of 5 times of beta. You know, this value here is 9.30 10 to the power 5, this is beta, okay, times of 1 by root of pi minus of, instead of this IERFC representation, we put this particular value which is 1 by root of pi e to the power of minus zeta square minus zeta times of 1 minus the error function of zeta here, okay, where we already know that the error function of zeta is actually a numerical integral of the type 0 to 2 pi or 2 divided by root pi 0 to theta integral e to the power of minus sort of, you know, x square dx. So, as I already had mentioned that you know, the error function is a numerical integral and there are values which are arrived at as approximation corresponding to the various values of zeta, you will have the different values of error function. So, the standard tables actually which looks at what is going to be the error function for x given a certain x parameter. So, x is zeta in our case, and we have to really iterate now from here that what is that zeta value corresponding to which if we outlay the value of the error function in our solution right here, okay, and we already know the value of zeta from which this thing would happen, okay, that would result in this could be this value could be treated as just zeta by 200, as you probably may be aware. Beta is actually nothing but 1 by 200 zeta, right. So, I am sorry, 1 by 200 zeta, I am sorry, 1 by 200 zeta, okay, from this expression here. So, we have everything in zeta on the right, and for a corresponding value of the numerical integral I should have parity here. For, you know, if we do like this by looking at the expression in the table, it so happens that corresponding to a zeta value of around 0.5, okay, somewhere between this and this, we would like to have, you know, if we wanted to just outlay this expression once more, 3400 equals 9.30 10 to the power of 5 times of 1 by 200 zeta times of 1 by root of pi minus 1 by root of pi e to the power of minus zeta square plus zeta times of 1 minus twice by root of pi integral 0 to zeta e to the power of minus zeta square d zeta, okay. We have, using the table and numerical integration, the zeta comes out to be 0.5, beta comes out to be 0.01, and if this satisfies, so you put the zeta value here 0.5, and you know, you can calculate this value, similarly this can be obtained from the table corresponding to a zeta value of 0. I'm sorry, this particular value 0.5. You find out a parity between the left side and the right side, okay. So, this whole expression becomes equal to about near about 3400. I am not going into the calculation details here, but the zeta is actually nothing but in this particular case, as you have taken zeta to be 100 or 1 by 200 times of root over 0.79 Tm. This was the beta value actually. So, the Tm value with a zeta of 0.5, okay, or a beta of 0.01 actually calculated by multiplying, you know, various factors. So, the Tm actually comes out to be from this expression as 0.00073. So, if you look at the expression that we had earlier and the way that we had predicted earlier for a semi-infinite case, you had a situation where the actual value which was obtained came as 0.0005 0.000053, okay, another 0, so 0.000053. So with the condition or with an assumption that the surface is semi infinite, obviously it resulted in a much smaller time frame for the machining to have happened in comparison to the case where there is a circular heat beam. So obviously heat conduction plays a big role here, and obviously the heat affected zone is very small in this particular case, with cylindrical coordinates defining the zone which is affected by the laser machining process. And one of the reasons why the time scales come out to be quite different, okay, from the ideal case of assuming a semi infinite surface. So as we see here, this is more accurate, this is more appropriate in terms of when the machining should happen, and typically, and the start of machining really is when the center of the spot on the surface of the material that is being machined comes to the melting point, and beyond that it is almost the way that heat conduction would happen from the surface onwards, and how the melting zone would recede, so that there is a cavity formulated. In case you have a through cut, there is always a question of how much material needs to be ablated out till and until the melt zone can go all the way up to the depth of the workpiece that we have been considering. So the idea is that the basic essence of the start of machining and the wait period involved therein for the temperature to reach the melting point is a very key thing in the whole laser machining process. Although it is not that big a number, but still it does matter, particularly in micro machining using laser, etc., where the samples that you are trying to make are really very thin, and there may be sometimes in hundreds of microns, and so there may be a possibility of arriving at a substantial amount of time needed to sort of wait till the melting zone or the melting temperature is hit upon, okay, before the machining can start to take place. So let us just now sort of compare that by a general approximation. Considering a flat beam on a, let us say, semi infinite kind of surface, the total time scale which we actually saw was very small, 0.000053 seconds, okay. This is quite different than the more accurate expression arrived at with circular boundary condition. So just assuming here that supposing if the power intensity is too high, if the power intensity is too high, so that the term here on the right side of the expression satisfies a condition 1 by root pi very greater than the let us say IERFC d by 4 root of alpha t. Obviously if power is very high, this t is small and this whole term here is big, okay. And so if I were to look at this expression, it is really 1 by root pi to the power of minus zeta square minus of the zeta times of 1 minus twice root pi integral 0 to zeta I to the power of minus zeta square d zeta. So as you may recall here, the so let me write this a little more appropriately. So this is integral of e to the power, let me write this here, minus zeta square d zeta, okay. So as you may recall, because the error function is sort of, you can see, say, an increasing function, you can see these tables to gauge as the zeta increases, the error function would kind of increase. So, obviously, this value right here, that is the 2 beta or 2 by root pi, this integral value of 0 to zeta e to the power minus zeta square d zeta is going to be bigger. Okay. So, this is going to increase with the increase in zeta, and so is this going to increase. So, you can say that there is a condition where because of the increased value of this negative coefficient here, and simultaneously this value is going to reduce because obviously is 1 by e to the power zeta square. So, this would be much smaller than 1 by root pi. Okay. So, this is a case which can hit upon when the power density is too high, particularly when the time Tm becomes smaller because of increased power density. Let us just look at a reverse case. Let us say, for example, there is a case where the power of the beam decreases, and rather than increasing, the Tm increases now because you are operating at a lower power. So, obviously, the time to wait before the melting temperature is hit upon is more. So, then in that event, the theta 0 t, which is again, let us just write that expression down fully, twice h root of alpha t divided by k times of 1 by root of pi minus 1 by root of pi e to the power of minus zeta square plus zeta times of 1 minus the error function of zeta. Okay. So, let us see how this behaves. Obviously, we know that zeta is actually the ratio between the beam diameter, okay, which is d divided by 4 root of alpha by alpha times of t, and as I have already increased or decreased the beam power, therefore, the Tm has increased. Okay. So, this value Tm right here is increased, because of which zeta should come down. Okay. So, this zeta is much smaller. So, having said that, now let us see that if Tm is more and the zeta comes down, how this equation is going to behave. So, if the zeta value is smaller, let us say if the zeta approaches 0, then this increasingly approaches 1. Okay. And so, we are left with twice h root of alpha t divided by k 1 by root of pi minus something which approaches 1 by root of pi. Obviously, if zeta equals or approaches 0, this guy approaches 1, plus the zeta times of 1 minus the error function of zeta, a value which is normally there. Okay. So, if this approaches 1, if this condition is obeyed, then these guys cancel out, and we are left with a condition here where we just talk about twice h root of alpha t by k times of the zeta value, which is again d by, or let us just write down the diameter as capital T as we have been following earlier. So, capital D divided by 4 root of alpha times of t times of 1 minus the error function of the zeta value. Okay. And we can easily cancel some of the terms here, and we can just try to convert this into h d divided by twice k 1 minus the error function of the zeta value, where the zeta is actually ratio d by 4 root of alpha t. So, having said that, now this is a kind of condition which corresponds to low beam powers, because the Tm value is reasonably high in this case, and therefore, for the low beam power case, the theta m equals theta 0 t, as such a power is hit upon, lower beam power is hit upon, is actually equal to h d by twice k times of 1 minus error function of d by 4 root of alpha Tm. So, this is the more simplistic form of the expression, and obviously the maximum value of this particular expression is 1 when the Tm value approaches to a very high value. So, if Tm is increased to a high value, so that d by 4 root alpha Tm, the zeta value approaches 0, then it is a case where I can say that the maximum for the lowest beam power case, okay, or we can talk about it as the minimum beam power which is needed. Okay, the minimum beam power needed would be corresponding to when the theta m becomes HD by 2k. This is again I am sorry to represent it as small d, this capital D that we are talking about here. Okay. So, HD by 2k, that is what the theta m value is going to be, and this is how you can estimate what is going to be the criteria corresponding to which minimum beam power can be used, laser beam power can be used for the temperature of the surface to hit upon the maximum temperature of melting. Okay. So, I can probably now write a little bit about this in low power cases or low beam power circular beam cases, as that the critical power that is needed HCR, which is the minimum input power needed to melt the material, is actually given as twice k theta m by d. D is the beam diameter, theta m is the melting temperature of the material, and k is the thermal conductivity. And so, below this critical value the melting temperature will never be reached. You can say that HCR is the minimum value below which machining cannot be done. So, by now I think it is clear that how we have expressed the one dimensional heat conduction equation in a circular beam case, and how we have tried to actually estimate the minimum power requirement that would initiate machining process to happen. So, I think in the interest of time we will close this module, but in the next module we will try to once again revisit this issue and do some numerical design problem where we see what is the minimum power which is needed, and then also try to look at what is the conduction aspect on the workpiece side that would happen in the melting zone, where there would be a heat transfer which would happen from the center to the sides. Okay. And then in that event we will try to again see or revisit what is going to be the effective power that is coupled into the system from the laser. With this I would like to end this module. Thank you for being with me. Thank you.